So while we're waiting for people to come in, let me just ask people, number one, was anybody able to take advantage of the good weather on Saturday? No. There was good weather on Saturday, in theory. And and everybody has downloaded the notes for today, right? Or who has not downloaded the notes for today's class? Okay, so you're supposed to download the notes, and I don't have extra copies. So maybe you can look on with someone sitting nearby when it comes to certain things we'll be doing. And does anybody have any questions on particular matters? Yeah.
I'm the one that has a conflict with office hours and this.
Right. Okay. So, well, so Andrew Menard is the TA, and he should be here momentarily. I guess he's running from a class across campus. So there's one other person whose situation I think is like yours. Okay. Huh? Okay, so in other words, so who here cannot make either office hours or recitation? Okay, three people. Okay, so what I'm going to ask you to do is meet with Andrew after class today and come up with a time. No, he's going to. He wants to. What we talked about as a possible solution is to schedule another office hour segment on Fridays. Okay, and he will discuss various options with you. But if we do this through email, it will get resolved by August. So the three of you should stay after class and talk it over with Andrew, who should be here. Who should be here in theory. Okay.
So recitation is kind of exchangeable with office hours?
I wouldn't say that, but in your case it will be. So in other words, that the bottom line is there is no recitation time that everybody can make that is not horribly inconvenient. I mean, if we had recitation Friday at 7 a.m., everybody could make it, and no one wants that. Okay. So, but and to tell you the truth, I don't actually know historically how much recitation has proven useful to people. So, but my sense is you could probably accomplish the same thing in office hours. That's the idea, that office hours is probably a good substitute. For all I know, maybe even better. So, okay. And then you have homework due today. So let's just make sure you drop it off when you walk out of the classroom. You don't need to turn it in right now. And also today, you're probably wondering why there's I'm wired for and being filmed. This is part of MIT's illustrious OpenCourseWare project. So how many of you are not familiar with OpenCourseWare? Okay, so you don't know what it is. And where are you at MIT?
I'm an air usher.
Okay, so first of all, you could lose your registration status just for not knowing what OpenCourseWare is MIT's big thing where instead of trying to make money by selling distance ed or whatever, MIT's decided that and they hope to get like over 90% faculty participation eventually. Just why don't faculty just post their materials in a well-designed way with official institute support so that anybody in the world can see what's going on in your course. And it's sort of saying that it's not saying you can get an MIT education, but you can see what we do. So people can see the material here, and then I think they're going to be filming 3 lectures here just to illustrate how a professor reacts to brilliant students. So, and with that in mind, let's start today's lecture. So let me ask you, yeah. Yeah. Okay, so, all right, so Thank you. So the next homework assignment should be due next Tuesday, but this class, I know you're disappointed, is not going to meet next Tuesday because next Tuesday MIT's Monday class meet, right? That's the way it works to get parity in the schedule between Monday, Wednesday classes and Tuesday, Thursday classes. So we meet this Tuesday and Thursday, and then we don't meet again until next Thursday. So next homework will be due, instead of next Tuesday, next Thursday, the 19th. Okay? And what I want you to do is exercises 3 and 7 from the handout on Newton's method, and exercises 1, 2, 14, 17, and 18 from the quadratic forms and functions. Okay? And your name is?
Hi.
Hi. Okay, so hi, I couldn't tell, but it looked for a moment like you were going, whoa, that's a lot of numbers. Is that what you were doing?
Yes.
Okay, so this is how I got to be a professor. Okay, so hi, it turns out you're wrong. Okay, I mean, it's actually a lot of numbers, but it turns out these are all the right numbers, because I will just tell you this. 1, 2, and 14 are like one-line proofs. Okay, so these are just little things that I wanted you to see. Okay, so it turns out the actual homework is really 3, 7, 17, and 18. So these should be, these combined should take you 6 minutes. Okay, the others combined, who knows, 6 hours, 12 hours. You lose track after a while. So, yes.
Did you cover what the 1, 2?
Yeah. Okay, so what does this mean? So let me ask you this. How many of you downloaded the lecture note last night? How many of you downloaded the lecture note on Newton's method last night? You lectured when this morning?
Or about half an hour ago.
Okay, so question 7 in the Newton's method notes, says proof proposition 2.1 in the notes. And if you were to look at proposition 2.1, depending upon when you downloaded the notes, it either says prove the following 2 things are equivalent, or prove the following 3 things are equivalent. Okay? Because I took out the third thing, even though it's true. I thought you don't really need to prove it. Okay? So that's what this means. That you should prove that 1 and 2 are equivalent, and if you have 3 in your notes, you don't have to mess with it. Okay? All right. So I'm going to ask you to, the 2 of you, come right in front of me and sit over there. Okay. All right. So I want to talk about Newton's method, and let me just ask anybody who has used Newton's method. Okay. How have you used Newton's method?
Pretty great sense.
Huh?
You mean what particular?
What was the application?
Classification.
In pattern classification? Really? Newton's method? And so what kind of problem were you?
Logistic regression.
Okay, all right. And you had your hand raised.
Maximum likelihood statistics type.
Okay. So Newton's method has been around, actually, ever since Newton, okay, who came up with it. And actually, I don't even know, but I imagine that Newton came up with it for one-dimensional problems. And I think it was Raphson, a mathematician named Raphson, right around the time of Newton, who extended it to multidimensional problems. But we're going to look at it, actually, in the context of optimization. Okay. So Newton's method is, I have to give you a history, because I started teaching this course for the first time in 1986. And Newton's method has changed, oddly enough, since 1986. So it's been 18 years, and Newton's method, instead of being actually sort of a method of last resort, because you had to solve, quote, large, unquote, systems of equations, like 500 by 500 systems of equations, okay, now is a method of primary resort, because all you have to do is solve large systems of equations, like 50,000 by 50,000, right? So computational power has changed the role that Newton's method plays in optimization. Okay, so that's one thing. And the other is interior point methods, which we will learn about in depth after the midterm, okay, rely on Newton's method. And interior point methods now are the dominant conceptual lens in convex optimization. And so Newton's method is really important because Newton's method is what drives interior point methods. Okay, so what is Newton's method? So if I have an unconstrained problem, like minimize f of x, subject to x is in some open set, which let's just take that as to be Rn right now, I can really think of f of x at a given point x bar. So I have a given, my current iterate of my algorithm is x bar. Okay, I'm going to build a Taylor expansion. So I got the constant term by gradient and by Hessian. And I'll just put, it's approximately equal to this. Okay. And actually, maybe I'll just call this whole thing h of x. And so I build a quadratic model, and then I solve my quadratic model exactly. So how do I solve my quadratic model exactly? So I set the gradient of this equal to 0. So, and now as the course develops, some of you already are very fluid with, you know, gradients and Hessians and everything else, and others of you are a little more stale, but you will become fluid. So Andrew, I'm going to suggest you roll on over here because we have, okay. And a note for you to stay after class to talk to the 3 students who have conflicts. Okay, great. Okay. So some of you are already fluid with these. Others of you, it's just going to take some practice. Okay. But what is the gradient of this function at x? Any of you? So if you raise your hand now, I promise I won't call on you for another 2 minutes or so. Okay. What's the gradient of this function? Yes?
That's del fx
Yeah?
at x bar.
Okay. So the gradient of h, right, is, okay, right?
Plus Hessian at x bar
Uh-huh.
minus x bar.
Times,
X minus.
good. Okay. All right. So that's the gradient of this quadratic approximation. So let's set that equal to 0 and solve. Okay, and if I solve this, and this Hessian matrix is invertible, I get x minus x bar is equal to minus h of x bar inverse times the gradient. Everybody with me? Okay. And I can really think of this as my Newton direction, or Newton step. Okay. So, and that leads to a simple algorithm, which I outlined on the bottom of page 2. So actually, let me try and experiment with using the overhead to go through more mundane things. So who can't see this? Who can't see with the aid of their notes, at least, what's going on the bottom, these last 4 lines? Really tell me, because Kate, can you see this? Okay, all right. So this leads to the following method, right? It just sort of says, look, here's my initial iterate x naught, set my counter to 0, compute the Newton step, which is minus the Hessian of the current iterate inverse times the gradient. Okay? If the Newton step is 0, then stop. Otherwise, and we're going to say set your step size equal to 1, and just update. Set the new point to be the old point plus the Newton step. Okay? This could be modified where instead of taking the full Newton step, you did something else along the line. Maybe you took half the Newton step, or maybe you did a line search along that direction. We'll get to that in a little bit. Okay, that's Newton's method. So you tell me, what immediately strikes you as one important feature of the method, computationally? Yes?
You just have to solve a linear system.
You just have to solve a linear system. Okay. And how easy is it to solve linear systems? Who finds solving linear systems easy? Okay, you do. Okay.
Do I know?
What? Or do you not? I don't know. Okay. But actually it depends on the system. If you have a 100 by 100 dense system, no big deal, right? If you have a 10,000 by 10,000 dense system, you're in trouble. Okay, you can't actually solve it explicitly. You're going to need some kind of iterative method, or you just might, Gaussian elimination is going to break down. It's just going to involve too many operations. So I'm just saying, in a sense, the bottleneck of Newton's method is that you have to solve a system of equations from scratch at each iteration. Okay, so that's, and what we're going to see, in fact, is that although that is, on a relative basis, a lot of work for an algorithm, okay, maybe doing all that work, you're learning a lot. Okay, so that you're taking full advantage of a lot of information. You're taking advantage of both the gradient, knowledge of the gradient, and knowledge, you're taking advantage of first and second derivative information about the function. You can think of it that being a good thing. Okay? All right. So, and then I remark at the top of page 3, say, right, the method actually assumes that the Hessian is invertible at each iteration, which it might not be. Okay, so we're going to look for classes of problems in which we can guarantee that, or we're going to need some mechanism for enforcing that or modifying it so that whatever we do, we've got something that's invertible. Okay. I also remark at the top of the page, right, that there's no guarantee as I've written this method that my objective function decreases. One would think in any intelligent algorithm, as I go from iterate to iterate, I'm improving my objective function. Okay, but so far I have no guarantee of that here in this method. Okay, so we'll talk more about that later. And then I state the next point is that step 2 could be augmented by a line search. And let me tell you what I mean by that. So that if I think of a method, say here I am at my kth iterate, okay, in a sense, one can think of an algorithm as just being something that at each iteration, I first compute a direction in which to go in. So I have xk and say I have this direction, dk. And then I need a mechanism for figuring out how far I should go in that direction. Okay? And if I go, my step length is 1, that means take the full Newton step. Okay? I could augment it and try and solve the following one-dimensional problem, namely minimize over alpha xk plus alpha dk. And so to say, okay, along this whole line here, I am going to look for the one-dimensional minimum of my function. Okay, and actually there's a homework exercise that we decided not to assign where I could have asked you to prove the convergence of Newton's method with an exact line search. Okay? So that's sort of the key features of Newton's method. Okay. So even before I go any further, why is Newton's method, do any of you know the answer to the following question? Sort of, what is the most well-known, very attractive feature of Newton's method, at least from a theoretical point of view? Any of you know? Okay, it actually, not necessarily, but if it does converge, it converges at an extremely fast rate. Okay, an extremely fast rate, and we're going to see that shortly. Okay, but before we get to that, let me go over some other features of the method. Oh wait, hold on. Okay, so I'm going to erase this and put here, D is times. That is the Newton direction. Okay? And the first thing I'm going to prove to you before we talk about convergence rates is proposition 1.1. And for that, we're going to recall, so, right, we say a matrix is SPD. That means symmetric and positive definite. And what does positive definite mean? I don't want to do the same old people. So, Andrew, you're the TA. The person next to you is?
Len.
Huh?
Len.
Len. Okay, what does positive definite mean?
You multiply by a vector to the left and the right. It's always going to be greater than 0.
As long as the vector is?
Non-zero.
Non-zero. Very good. Okay, so that's what it means, symmetric, positive, definite. And so proposition 1.1 says that if the Hessian is SPD, okay, then the Newton step and D is not 0, and my Newton step is not 0, then D is a descent direction. And recall for me informally what it means for a direction to be a descent direction. I should say a descent direction at x. What does it mean to be a descent direction at x?
The value of the function is lower than the value at x.
Okay.
So
For as long as I go a short enough distance. Right. It is a direction of decrease in the function. Okay. So how do I prove that? Well, first, what's one way I can prove it? Okay. We had a proposition last week that gave a sufficient condition for a direction to be a descent direction. And does anybody remember what that was? A direction is always going to be a descent direction if it satisfies Katie. Nah, I don't know what you mean by that, but if it's but yes, if it makes the correct inner product with the gradient. Okay, so it's something that was gradient related, anyway, to borrow a phrase from Dmitry Britsakis. Okay, so if my direction makes a negative inner product with the gradient, then it must be a descent direction. So I need to prove that D transpose del f of x is less than 0. Okay, that's what I need to show you. But that's somewhat straightforward. And so watch how I'm going to do that. So I'm running out of boards here. Let me try something here. Hold on. Whoops. This is like it's a Woody Allen version of a... Okay. Can everybody see the bottom of that screen? All right. Let's try seeing. All right. So... So watch this. So by definition, okay, I will have that my Newton direction dot producted with the gradient is minus, since I'm taking the transpose, it's minus the gradient times the inverse of the Hessian times the gradient, right? Now let's see. This would be negative under what condition? if the inverse is positive definite, right? If the inverse is positive definite, this is going to be a negative. This whole thing is going to be negative. Okay, but we said that the Hessian was positive definite. Okay, so now I've just got to show you that in fact the Hessian is positive definite if and only if its inverse is positive definite. Okay, and that's real easy. So now I need to show, in order to complete the proof, so this will definitely be true if h of x inverse is SPD. Okay, but now why is that true? So watch this. So I know that h of x is SPD. Okay, so now take any vector v. Okay, so pick a v, and then I know that, for instance, I know that 0 is less than v. Yeah, watch this. Sorry. So v h of x inverse v is equal to vt h of x. No, how do I do this? Oh yeah. Vt h of x inverse, vt h of x inverse v. Okay. That's true. Okay. And then this, I know, is strictly positive. Oh, so I wanted to prove that this was true. Yeah. This is equal to this, and this is positive. This is strictly positive because this is just this vector hit with the Hessian hit with the same vector. Okay? And so that's the proof. Okay? So, but now what have I shown you? Okay? All I've shown you is that the Newton direction is a direction of decrease. I haven't shown you that my new point is going to have a better objective function value, right? All right, everybody see the difference? Okay. All right, so now let's talk about rates of convergence. And this is important not just for this lecture, but actually for the rest of the course, because we can prove a lot of things about that. I can prove for a lot of algorithms that they converge. And you might sort of think, that's great, all I need is convergence. Okay? And so, but for example, suppose the convergence rate, suppose I go to this wall. I can walk to this wall at the following rate. At each step, my distance from the wall is 1 over square root of k. Okay? How many iterations is it going to take me? So clearly this goes to 0 as k goes to infinity. So at the kth step, my distance is 1 over square root of k. How long is it going to take me until I'm within, say, 10 to the minus third of the wall? Who am I up to? Your name?
Craig.
Craig.
It's going to take 10 to the minus third is going to take 10 to the 6 k's.
10 to the 6th. Okay. I don't have time for a million iterations. Okay. On the other hand, right, if it was 1/10 to the k, okay, now how many iterations is it going to take? Yes?
3.
3. There you go. So I just want so different iteration, different rates of convergence. So we'll say that the series 1 over square root of k converges much slower than this series. Okay? But we have general classes of convergence, and so let's talk about that for a minute. So suppose I have, do this over here. My notes. So I have a series, S sub I, okay, and say that converges to some S bar. Okay? And these are just scalars. Okay? So then I'll say that my series exhibits linear convergence if the limit as I goes to infinity of S sub I plus 1 minus S bar over Si minus S bar is equal to some delta that's strictly less than 1. Okay, so what does that mean? That means that you could think of the numerator being how close am I at the next iteration compared to how close am I at the current iteration. And if in the limit this ratio is some number less than 1, we call that linear convergence. Okay? So that's linear convergence. Now let me give you an example of linear convergence. For example, S sub I equals 1/10 to the I. Okay? Or any number less than 1 raised to the ith power has exactly this convergence rate. SI, and here, in all the examples, by the way, S bar is 0. Okay? So SI plus 1 over SI is 1/10 to the I plus 1 divided by 1/10 to the I, which is just 1/10. And so we call that linear convergence. What's interesting is, what's a much different phrase you might use to characterize the rate of decrease of this series? Exponential, sometimes people call it geometric, okay? But it's actually called linear convergence, okay? If, on the other hand, delta is equal to 0 here, okay, which this series doesn't exhibit, okay, that's called, I love this phrase, it's like right out of the 60s, that's called superlinear convergence, okay? And so let me give you an example of a series that has superlinear convergence. 1 over I factorial. Okay, let's do the computation, and I'm up to you. Yeah. So what is SI plus 1 over SI?
I?
1 over I.
1 over I.
Yeah, so right. S sub I plus, actually, 1 over I plus 1. So you almost had it. You were just wrong in every aspect. Okay. So, right, the ratio of the current distance from the limit point, the next distance to the limit point to the current distance is 1 over I plus 1, and that's going to 0. So that's superlinear convergence. Okay. Quadratic convergence is this. Okay. And that sort of says, in the limit, oh no, did I get this right? I thought there was something wrong. Okay. And so this says, in fact, that in the limit, at the next iterate, it's going to be something like a constant times the square of the previous distance. Okay? So that's quadratic convergence. So let me show you an example of quadratic convergence. Okay? So quadratic convergence would be 1/10 to the 2 to the I. Okay? So this clearly, as I goes to infinity, this number is getting huge. This is converging to 0. But it's really converging fast. I hope you see that. Okay? So for example, S sub 1, S sub 0 is 1. S sub 1 is... Huh? 1/10. Oh no, 0.1. Thank you. 0.01. Okay. What's S sub 2? So who am I up to? You. If you could please tell me your name.
Oh, I'm Gordon.
Gordon. I forget your name.
Pete.
Pete. Okay.
So 0.0001.
Yeah, 0.0001. Okay. S sub 3.
I think there's 7 zeros in the middle.
There you go. Good, good. Okay. Okay, etc. Okay, and so we get within machine precision really fast. Okay. And so at the next iterate, instead of 7 zeros, there would be how many? 15. Okay. So this is really going to 0 quickly. Okay, so that's quadratic convergence. Okay? And now I'm going to show you a theorem which is going to be our main result here. I don't know how to do this. Okay. And so this is the main result about what we know about Newton's method. And then if you really want, you could, people have spent careers trying to refine this theorem, okay, under which cases it works better. But let's just take a look at the structure of this theorem, okay, so that we're going to attack this in several ways. But to me, this is one simple concept, okay. If a bunch of stuff holds, okay, and we're going to, all right, so just stick with me on this, okay. If a bunch of stuff holds, okay, and my current iterate is x, my next iterate, you can either think n is the next iterate or n is the Newton iterate, okay, which is the current iterate plus the Newton step, okay, okay. Then, so one thing it says is that, oh, I didn't even tell you. I got to put up here. Sorry. X star is a value for which the gradient is 0. Okay. If a bunch of stuff holds, then my Newton iterate is, I think there should be a less than sign. Nope. Yeah, right down here. Okay. My Newton iterate is closer to a point where the gradient is 0 than my current iterate is. That's what the second statement says. Okay? And gamma was something that we supposed that the current iterate was less than a distance gamma from this point where the gradient is 0. Okay? So that's 2. 1 says, in fact, actually, the next iterate is less than or equal, the distance from the Newton iterate to the optimum is less than or equal to the distance of the current iterate squared times this guy. And then the third statement basically says I can replace this guy, which depends upon the current iterate, with just some absolute constants. And so it's the third statement here, which is explicit quadratic convergence of Newton's method. Okay? Everybody with me? So now let's look at, well, the thing about a bunch of things hold. Okay? So let's see what these things are. Okay, the first thing that holds is that I have a point x star at which the gradient is 0. Think of that as a local min or a local maximum, but let's just think local minimum. Okay? So I'm just going to call it the local minimum. Okay? And this says that not only is the gradient 0, but the Hessian is not too, you can think of the inverse of the Hessian is not too big. There's some positive number so that the norm of the Hessian matrix is not too big. Now, what do I mean by the norm of the Hessian matrix? And that I'm going to need to put somewhere. I'm going to put the norm over here. So the norm of a matrix, what's called the operator norm of a matrix, is the maximum norm of mx subject to norm x less than or equal to 1. It just sort of says, okay, how big, when I think of m as a linear operator, and I hit any x with norm less than or equal to 1 with m, how big could it become? Okay. I hope that coincides with the definition. Yes. Oh, less than or equal to 1, equal to 1, doesn't really matter. Yeah. I don't care. Okay. All right. So this says, right, and this is a norm on linear operators, on matrices. So it may not, you look a little confused or no? Okay. All right. So this is a norm, and it says the norm of the inverse of the Hessian is not too big. That's the first condition. Okay. The second condition says there exists a beta. You can think of that as the neighborhood. So that so long as x is not the distance from x to the optimum is at most beta, this condition holds. What is this kind of a condition called? Any of you know the name? Yes. It's called a Lipschitz. So a Lipschitz condition, when we say something is Lipschitz, it means that we can bound relative changes. So this says that the Hessian is Lipschitz. And in fact, that's why I used a capital L here for Lipschitz. Okay, so this says, look, if I'm sufficiently close to x star, the difference in the Hessians is bounded by some absolute constant times the distance, how far x is from x star. Okay, you have a question? Okay. Okay, so that's that. These, by the way, ladies and gentlemen, this is all technical junk, in a way. So that, notice, at a certain level, it becomes valuable to study the interplay here. But right now, because I'm going to then give a loose interpretation of this, and it's going to be very loose, okay, shortly. So this says, the first condition says, the inverse of my Hessian is not too big, which means my Hessian is, I can bound it away from being singular. You can think of it that way, okay? And this says, in a neighborhood around x, for a point sufficiently close to my point where the gradient is 0, my Hessian is Lipschitz. And then the third condition says, my current point is really close to x star in the following sense. Its distance from x star is, in fact, strictly less than some gamma, which is going to be the minimum of beta and 2h over 3l. Okay? Why the 2 and why the 3? Because. Okay? Because the arithmetic will work out nicely. Okay? So this says, so now let's recap. This says if my Hessian is well behaved in a neighborhood of x star, if I start sufficiently close to x star, and if my Hessian, in fact, not only is well behaved in a neighborhood, but I can that it's non-singular. Okay, all right. Then I get quadratic convergence. Okay. All right. Now, I'm going to prove this later in the lecture. Okay. But I just want people to digest it for a little bit. And I want people to see a little bit about it. So let me do a simple example so people see what's going on here. So my first example is going to be a one-dimensional example, and then you'll be able to see exactly what's happening. Okay? And so for my one-dimensional example, I'm going to choose the function, and I'm up to you. Your name?
Shobit.
Shobit. That's right. Shobit. Okay. So suppose, for example, I have a one-dimensional function. F of x is 7x minus the log of x. Okay? Now, what's the instead of gradient, we'll talk about first derivative. So what's the first derivative?
7 minus 1 over x.
Good. 7 minus 1 over x. And what's the second derivative? 1 over x squared. Okay. And now your name is?
Rags.
Huh?
Rags.
Rags?
Yep.
Or, okay, Rags? Okay. Rags. So then what's the Newton direction going to be at x? Minus?
7 minus 1 over x.
Okay.
Times 1 over x squared.
Over what? Times 1 over x squared?
Inverse, yeah.
1 over x squared inverse, which is just x squared, right? So in fact, that would be the Newton direction, okay? And so that says then the next iterate, so xn is going to be x minus this. And then you can work this out and have appropriate adjustments here, okay? So, did I? X minus, I got it right. Yeah, I got it right. So I can program that on my calculator, right? Even my calculator which is 20 years old. Okay? And so what does it look like? Well, let's take a look at what happens with our iterates, if we can actually get the screens to work. Oh, no. Now I got to remember, screen left is your screen left. Okay. So watch what happens over a sequence of iterations. And now I got to turn off the lights. Huh. First time, every time. Okay. So first notice that, watch this. If I start at x equals 0, what is this whole thing? And assuming I clear this so that this is x minus 7x squared plus x. Okay? What's the next iterate going to be? 0, right? So it's going to go nowhere. So if I actually start at 0, all my iterate values are 0. I've learned nothing. Okay? Suppose I started at point 1. Okay? Here's the sequence. Now, who sees the quadratic convergence there? And how do you see it, if you do see it? And I'm up to, I should know your name by now, but I don't. Peter. Okay. And you're Peter as well. So Peter, how do you see the quadratic convergence, or do you?
I don't know.
You don't. Who does? Who does? Okay. And are you Claire?
Yeah.
Okay, Claire. How do you see the convergence, the quadratic convergence?
Oh, just seeing, maybe I'm not seeing the right thing, but just seeing these exponents doubling. The 10 to the 11th, 24.
No. I'm looking at this column. Sorry, these are 4 different starting points of my algorithm. I'm sorry. So if I start at 0, I just stay at 0. If I start at point 1, at the next iterate it is exactly 0.13. It then goes to 0.1417, etc. Okay. Katie.
Just take the next step and divide it by the square of the next one, and it's clearly we're starting with 1.
Yeah, okay, but without even doing any arithmetic, who can see it? Yeah.
You can count the number of decimals that stay the same for the next line.
Yeah. And the other thing is you can cheat and look down here. All right, now watch this. So you cheat and look down here. Here's going to be the answer. Okay, this is 1/7, I think. Yeah. The answer is 1/7. Okay? And now let's count how many digits of accuracy I have. And that's sort of a rough estimate. So watch. 1, 1, 2, 4, 7, like 11, and then it's the same. So I mean, I'd have to go out beyond machine precision or something like that. But in other words, it's basically the number of digits of accuracy is doubling at each iteration. That's quadratic convergence. Okay? Here's what happens if I start the algorithm at 1. Okay? 1, next iterate is -5, minus 185, etc., etc. Now I'm getting the quadratic convergence. Okay. That is, each is some constant times the square of the previous distance, but that all those numbers are bigger than 1. Okay, so this is getting junk. This is essentially junk because it's doing nothing. Okay, this says if I start in a neighborhood of the solution, I'll hone in quickly. Here I'm starting in a neighborhood. This one's going to make it, but it's going to take a lot longer for it to get warmed up. Okay, because I will just tell you, I happen to know a lot about the function 7x minus log x. Okay, why? Well, one summer I didn't have much else to do. Okay, think of it that way. All right? And so I know, for example, that the range of quadratic convergence, okay, for Newton's method, is precisely the open interval between 0 and 2/7. As long as I'm in strictly between 0 and strictly less than 2/7, quadratic convergence will kick in. Okay? And here I start very close to the end there. And it takes me a while to get warmed up, but then pretty soon we start to see this behavior. And again, I want you to think that when things are converging quadratically to the solution, essentially, you're doubling the number of digits of accuracy at each iteration. What is linear convergence doing? Yeah.
That's one digit of accuracy.
That's right. You can think of it adds a constant number of digits of accuracy per iteration. Maybe a half, maybe one, who knows, but whatever. So that you can think of, right, whereas this one is doubling it. Okay? Good. So that's a one-dimensional example. It'd probably be a good idea to look at a multiple-dimensional example. And here's a multiple-dimensional example. Oh, whoops. Yeah. Here it is at the bottom of page 5. So, minus the log of 1 minus x1 minus x2 minus log x1 minus log x2. Okay? The gradient, I mean, all this is, you know, you could do it in MATLAB, I guess, or Mathematica to do the automatic differentiation. Since I don't actually know how to use any of those tools, I did it by hand. It was a good summer. So here's the gradient of that function. Here's the Hessian. It's 2 by 2. So we've got a two-dimensional problem. And I will just tell you the optimal solution is a third, a third. Okay. And here, for example, I started Newton's method. And so by the way, if I don't know how to use MATLAB, how did I solve this problem? Right, I've got to invert a matrix and all of this stuff. Right, so right, Peterson says you got one of your graduate students to do it. Okay, that's I should have done it that way, but believe it or not, I programmed this in Excel because I'm a Sloan professor. So everything has to be in a spreadsheet. So anyway, so I started at this point here at x1 equal 0.85, x2 0.05, and here I just keep track of the first coordinate and the second coordinate. And also here I kept track of its Euclidean distance to the optimum. Okay? And all three will exhibit the quadratic convergence. And you can see here, since what? At iteration 3, I've picked up the first 3. Now I have 2. Now I have 5. Now I have 8. Now I have like 16. It's like, again, doubling. It's the same thing is going on with the second coordinate. And this distance here, you can see, by the time you're getting an exponential, it's say 10 to the minus 5. E. I think this means this should be 10
That's what it means.
in Excel.
Well, in MATLAB too.
Oh, so maybe I did do it in MATLAB. I mean, maybe it was, oh, okay, maybe it was Fernando Ordonez who did it for me. Okay. All right, that would explain it. Okay. Peter, thank you. Okay. So the convergence rate of the method is quadratic. Okay. By the way, so these examples are very nice, but let's just be a little critical. So what's one drawback of the method that you see from this? Huh? Yeah, and your initial point has to satisfy all those conditions. So actually, let's look at those conditions. All right, I got it this time. So these conditions, in a sense, I would just sort of say, rather than belabor the point, these conditions are existential, right? We never know H, because if we knew H, I mean, we typically don't know H because we don't know X star, okay? And that means we don't know beta, we don't know L, we may know L, but we don't know beta, we don't know gamma. I'm just saying these are existential conditions that say if life is very well behaved near the optimum and I'm already near the optimum, I will really get near the optimum, okay? That's just sort of, think of it that way, all right? The other thing, though, you should know is there is an important class of functions for which this theorem can be made a lot more constructive. Okay? And I will give you 3 functions for which we can know all these constants and other things beforehand. Okay? And we will visit this when we study interior point methods. And those functions are minus the log of x. Don't write this down unless you're just you're not responsible for this, but you can write it down if you want. Okay. Minus the log of x minus the log of t squared minus, so minus the log of xj, think of it that way. Minus the log of t squared minus xtx for t positive. Okay. And minus the log determinant of a matrix X. So it turns out these three functions we can say a lot more constructively about Newton's method. Okay? And not only that, we can say things constructively about these, but then if we add these functions to one another, okay, we can say, well, that is, these functions and all of their combinations. Okay? And believe it or not, it is these three functions that are at the heart of modern interior point method theory. Okay, so that's just a little fact. Okay. So I'm looking at page 6, and I want to cover these bullet points. So we typically never know the constants beta, h, or L. There are some amazing exceptions, and these three are among those exceptions. Okay? There's a curious fact which is sort of lost on a lot of people, which is the rate of convergence, in a sense, is independent of the choice of norm, but the constants are not. And that is a mismatch. Okay? That is not the case for these three functions. The statement I just said actually was a very deep statement. Okay? But I just want to leave it at that. Okay? So, two former Soviet Union mathematicians named Yuri Nesterov and Arkady Nemirovsky wrote a 500-page book resolving that question. Okay? And it's a fantastic book. Okay? And then another very brilliant optimization professor at Cornell wrote a 120-page book just trying to make sense out of the 500-page book. Okay? And that's a brilliant book. Okay? That 128-page book is so easy to read. Andrew and I spent a semester and a half just trying to figure it out. Okay? And we did, actually. So, or at least he did. So here, also, Newton's method, we did not assume any convexity, only that the Hessian matrix was invertible. Okay? And what else do I have here before we get to the proof? Okay. So, note from the statement of the convergence theorem that the iterates of Newton's method are equally attracted to local minima and local maxima. That is, the statement of the theorem just says, I'm getting attracted to a point where the gradient is 0. Okay? My next point says that when we apply the method in practice, sometimes we hit points where the Hessian becomes singular. And when that's the case, usually sort of, software is written so that, if the Hessian is sufficiently singular, then we add some epsilon times the identity matrix to it. Okay? And then that's called like a quasi-Newton method. And there used to be an entire field called quasi-Newton methods. How many of you know anything about quasi-Newton methods? Okay. Your name is? Steve? And what do you know about
I only remember hearing it in this course.
You heard it in a what course?
Previous course on context optimization.
And who taught that? Was that here at MIT?
No, Stephen Boyd's, yeah.
Oh, okay. Oh, okay. So, and what did Professor Boyd say about quasi-Newton methods?
I think we used them quite a bit. We tried to.
Really?
Yeah, I think so.
Okay. All right. I'll have to talk to Steve about that. So quasi-Newton methods used to be all the rage. So what they are is it's sort of thinking, so go back 15 years in computing power. Okay? You don't want to solve large systems of equations from scratch at each iteration. So I'm here, I solve my large system of equations, I get my Newton direction, then I go over here. Okay? Now, instead of here building my Hessian and inverting it, I instead use information about this Hessian, combine it with information about like the gradient here, and do some other thing to save a lot of work. And unfortunately, that's all I know about quasi-Newton methods, okay? Except just that they are designed, they don't do full Newton steps, they don't do complete Newton steps, but they save on work. Claire.
Actually, I was just going to ask, so like, are there variants where instead of adding epsilon times identity, you add like epsilon times the Hessian at step k minus 1?
There's a whole, but I mean, my sense is there's literally dozens of quasi-Newton methods. Yeah. I actually have some lecture notes somewhere on quasi-Newton methods. I should try and dig them up one of these days. But I don't see them used very much anymore. Again, because computational power is such that they're not as relevant at the moment as they used to be. By the way, Arkady Nemirovsky is going to be giving a talk at MIT on, actually 2 talks, March 17th and 18th. So that should be a big event. This guy is a giant, really, in the field of optimization. Yes?
So you just said that we only assume like that Hessian is non-singular and not badly behaved, but didn't we assume that Hessian is also positive, definite, and symmetric?
Only in the result that states that if it was symmetric and positive definite, we had a descent direction.
Yeah.
That's all, but nowhere in this theorem. Not for the quadratic convergence theorem, just for the theorem about that we get that it's a descent direction. That's all. So this theorem is irrespective of, yeah. Yeah. Okay? So the work per iteration is order n cubed because that's the work per iteration in practice for solving a system of equations. We're not going to do, how many of you know about what's called fast matrix multiplication? Okay, so we're going to ignore all of that stuff, okay, because that's what people do. Okay, and there's my comment about so-called quasi-Newton methods. Okay, so in order to prove the result, so now let me try and fashion a proof. And if I don't finish the proof in time, I'm going to try and finish the proof in time. If I don't finish it in time, you can read it in the notes, because I feel, at least on a superficial level, the proof is just the proof is not insightful unless you spend a lot of time studying these methods. Then you can see what's going on in the proof. Okay, but I think for the purposes of this course, I want to do the proof so that you can see that in fact it's true. Okay, but I'm not sure how much insight I'm going to be fashioning in this proof. But I'm going to need the following result. Okay, which is, that says the following 2 statements are equivalent, which you are going to prove, which is exercise 7 of the homework. That is, the norm of n inverse is less than or equal to 1 over h is completely equivalent to the statement that the norm of mv is at least h times the norm of v for any v. Okay? So that is exercise 7 in the Newton notes. And for those of you that came late, which is essentially all of you, but I'm not bitter, okay? So if some of you downloaded the lecture notes after about 10 a.m. this morning, you only have proposition 2.1 has only 2 parts. If you downloaded it before 10 a.m. this morning, it had 3 parts. And you only have to prove the first 2 parts. Okay. And I'll just tell you, this is an easy proof. There's no, you can, a freshman at MIT could do this proof. Okay. So it's, you don't need any heavy machinery to do this proof. You just need the definition of the norm. That's all. Maybe not a freshman. Maybe a sophomore. Okay. We're going to need one other piece of information to do the proof, and that is proposition 2.2. So proposition 2.2 states, let's see where to put it. Maybe I'll put it down here. Proposition 2.2 is a simple fact that relies on the fundamental theorem of calculus, which just says that the gradient of f at z minus the gradient of f at x is equal to the integral from 0 to 1 of the Hessian of x plus t times z minus x dt, times z minus x dt. So this is a matrix, that is a vector. Okay. Why is this statement true, by the way? Okay. So this statement is true. Just think of, let me just define the function of one variable t, phi of t, to be f of x, or sorry, the gradient of x plus t times z minus x. Okay? So everybody see this? Okay. Then who am I up to now? You've said a lot. Hi, right? Right? Okay. So hi, what is phi of 0?
It's a gradient of fx.
Right. The gradient at x. And Chris, what is phi of 1?
It's the gradient f at z.
Good. Okay. Great. And what is phi prime at t? What's the derivative of this guy with respect to t? So now, and I got to think about this. Now, what do I mean is, you can think of it as the derivative of the entire vector. Okay. Do you know?
It is z minus x
Okay. Times.
the of the gradient dt.
Good. Okay. It's f of x plus t times z minus x. Okay. Times z minus x. Okay. Oh no, sorry. What am I talking about? It's the Hessian. Okay. The Hessian evaluated here. Okay. And so now, by the fundamental theorem of calculus, I know that phi of 1 minus phi of 0 is equal to the integral of from 0 to 1 phi prime of t dt. Okay? So that's from the fundamental theorem of calculus. Okay? All right. Now plug in. So phi of 1 is gradient of f at z. Phi of 0 is the gradient of f at x. And then this is the integral from 0 to 1 phi prime of t dt. So that's that. Okay? So now let's do the proof. Okay? And I invite you to help me as I make errors in the arithmetic. And maybe I'll start over here. Okay, so here goes. Okay? So xn minus x star. So xn is my Newton iterate. Xn minus x star is just going to be, well, xn is just x minus the Hessian inverse times the gradient, okay, minus x star. So that's easy, okay. And now I'm just going to rewrite this a little differently. I'll pull my x star over, okay, and then I'll say this is plus the Hessian inverse times the gradient of f at x star minus the gradient of f at x. Why is this true? And I'm up to you. Your name is?
Ian.
Ian, that's right. What did I do here? What term did I introduce?
Gradient of f at x star.
Right. And I can introduce it because it's equal to 0. Okay, so, okay? So now this I'm going to write is this is x minus x star, okay, plus the Hessian inverse. And now I'm going to invoke that formula that I just erased, that just hid, this formula here from proposition 2, that the gradient of f at x star minus the gradient of f at x is going to be the integral from 0 to 1 of the Hessian at x plus t x star minus x, okay, this guy times x star minus x. Okay, everybody with me? Okay, but now I'm going to rewrite everything with the Hessian in front of it, and this is going to be the Hessian of x plus t times x star minus x minus h of x, okay, x star minus x dt. So what am I doing from this step to this step? And I'm up to, your name is?
Nicholas.
Nicholas. What am I doing in that step?
You introduce the Hessian of x
Yeah.
in size integral.
Yeah, I'm just taking this, pulling it over here, and I'm multiplying first by the Hessian inverse, then times the Hessian, etc. Okay? Okay. Now I'm going to take norms. So I'm just going to do some erasing here, just to make my life easier. So I have xn minus x star is this, then the norm of this is less than or equal to the norm of this times the integral of, and I'm going to take the norm of this thing, and then the norm of this. Okay? I think. Isn't that what I did? Yeah. Okay? Okay. And now I'm going to take this guy and pull him out. So that's just the norm of h of x inverse, norm of x star minus x, integral from 0 to 1 of this norm here. Okay? But the integral of this norm here, now I'm going to invoke my Lipschitz constant. And Katie, when I invoke the Lipschitz constant, what can I replace this by? Okay, L times the norm of this guy right here. And that guy right here, of course, that's, I'm going to do two steps in one. That's t times x star minus x, okay, dt, right? I could pull the t out, okay? So I get L times t times this. Then I can pull this out because it doesn't depend on t. So when I pull this out, I get a squared here and erase this here. Okay, so I've got LT dt. And this is just then going to be equal to, so what's the integral of LT dt from 0 to 1? I'm up to you. Your name?
Natasha.
Natasha.
It's just L over 2.
L over 2. Right. With the, yeah, L over 2. Thank you. Okay, so I'm just going to replace this by L over 2. Okay. So I've got this now less than or equal to this. Okay. I'm almost done, at least with the first result, and then the others will follow, trivially. Okay? So I've got this result here. Okay. What do I need? So now I need to replace this by something that doesn't depend on x, eventually. Okay? Now how can I do that? Well, follow me. And then now, so let me ask you this. How many of you downloaded these notes before, I don't even know when it was, maybe 10, I'm going to say 11 a.m. this morning. How many of you downloaded the notes before 11 a.m.? All right, so you have a slight typo in your notes. Okay. So let me fix, so now let me, I got to figure out how to manage these blackboards better. Let me just write this up here. Norm xn minus x star less than or equal to norm of h of x inverse norm of x star minus x squared L over 2. Okay? So that's what we've got. Now I want to replace that h of x inverse. But that's easy, so watch. Okay? Let v be any vector. Then I have the norm of h of x v. Okay, well that's equal to the norm of h of x star times v plus h of x minus h of x star times v. Nothing too deep there, okay? Except now I'm going to invoke some inequalities, and I'm going to pull this apart by the norm inequalities. I can replace this by, this is going to be the norm of h of x star v minus the norm of h of x minus h of x star v. Okay, so that's true. Whoops. Okay. Now, from this result here, I know the norm of h of x inverse is less than or equal to 1 over h. And now I invoke this equivalence here to say, well, that means that the norm of h of x times v is at least h times the norm of v. So this is going to be h times the norm of v. And in your notes, you just have an h here. You should put in a little norm of v there. Okay? And now, what do I know about this? Since x is sufficiently close to x star, I want to bound this by, and I'm up to you, the Lipschitz constant. Good. So this is going to be bounded by L norm of x minus x star norm of v. Okay? And that whole thing is equal to h minus L norm of x minus x star times norm of v. Okay? So now I'm saying, look, I got for any v, h of x times v is bigger than or equal to this guy times norm of v. Now I'm going to come back here and say, I'm going to go back the other way. So I have this kind of a condition holding here. I've got a matrix times norm v. Norm of mv is now this, is bigger than or equal to some constant there that's in parentheses times norm of v. That means the norm of its inverse is at most 1 over that thing. So this all implies that the norm of h of x inverse is less than or equal to 1 over h minus L norm of x minus x star. Okay? Now I'm going to substitute that back in here, and I'm going to get, I wish I wasn't writing down here, but I have no choice. That says norm of xn minus x star is less than or equal to norm of x star minus x squared L over 2 times this, which is L over 2 times h minus L norm of x minus x star. Okay? And that, ladies and gentlemen, is statement 1 right here. Okay? Everybody with me? Okay? So now I got to prove statement 2, then I'm going to prove statement 3. So here was statement 1. And can I make this lower? Yeah. Now I'm going to do statement 2, then I'm going to do statement 3. But you'll see, that's all our work. Okay? So I also know from this little mess in here, for example, if I multiply the left and the right by L, I will get that, in fact, L times the norm of x minus x star is strictly less than the minimum of beta L and 2h over 3. So I'm just going to say that's strictly less than 2h over 3. Okay. And so I can plug that into here, and then I get that the norm of xn minus x star is less than or equal to the norm of x minus x star squared times, well, my L is going to be, shoot, now wait a minute, what did I do here? Oh, yeah, sorry. Watch what I do, sorry. I'm going to write this as this way. I'm going to pull one of these guys from the 2 up into here. So this is going to be L times norm of x minus x star over the denominator 2 times h minus L norm of x minus x star. Okay? Now I'm going to do this substitution here over here, and I get that this is strictly less than norm of x minus x star. Then this guy is less than 2h over 3, and this is 2 times h minus 2h over 3. And this whole thing is equal to, so this happens, the numerator and the denominator are the same, and so this whole thing is the norm of x minus x star. Okay, so that just showed that, in fact, the Newton iterate is actually getting closer. Okay, that's all statement 2 says, is that this, in fact, is less than this. Okay? And then finally, for the third one, okay, I have the norm of xn minus x star. Okay? I invoke this guy right here. So that's x minus x star squared L over 2 times h minus L norm of x star minus x. And that's less than or equal to the norm of x minus x star squared. And now I'm going to substitute that. In fact, I just showed that this, whoops. Oh no, now I just substitute it in one place. So I get this times L over 2 times h minus, and then L times this is 2h over 3. And that whole mess is norm of x minus x star squared times 3L over 2h. Okay. So let me make some final comments. Okay? I show you this proof because you should see that it is straightforward. Okay, straightforward in the sense that it is not an exotic proof. Okay? So what have some people done with this proof? Some people have said, well, I bet we can improve this. You know, if suppose we make this function 3 times differentiable, and we have all sorts of exotic things, okay, which is kind of nice if you want to write papers in exotic journals, okay, which some people do, okay. But I would just say this, really, that is, for most functions, all we know is existentially is if I'm close enough, I get quadratic convergence. And the exceptions are this class of functions for which we know when we're close constructively, okay? And when we know we're close constructively, we know a ton of things, okay? And these functions that I wrote down the names of the 3 functions. I don't know, I think I might have erased them already. Yeah. Okay. But, so I'll just give you a flavor. For example, for those 3 functions, if you compute the Newton step, for any one of those 3 functions, watch this, okay? So if my function was one of those 3 functions and so, or some combination of them, okay, I compute the Newton step minus the Hessian inverse times the gradient, okay? I'll call that D. If I compute the Newton step and I take the square root, now, sorry, hold on, I got to think straight here, yeah. If I take D times the Hessian times D, and it's less than 1, I'm in the range of quadratic convergence. For those three, that's a very constructive method. It says compute the Newton step. If it's hit the Hessian from the left and from the right. If it's less than 1, we're in the range of quadratic convergence. And we know all the constants for quadratic convergence as well, for those functions. That's later in the course. Okay, what are we going to do on Thursday? On Thursday, we're going to learn some stuff about quadratic functions, which are going to help us to evaluate other algorithms, in particular the method of steepest descent. Okay. Now we're going to learn on Thursday about eigenvalues and eigenvectors and all sorts of cool things about quadratic functions. So what I want you to do now is, as you leave, drop off your homework right over there, and then the students that have conflicts with recitation, stay behind and talk to Andrew. So thank you very much.